All right, well, thank you. I guess we've all made it almost to the end here, so I hope you'll be able to make it through my talk without feeling too hungry here. But a big thank you to the organizers for putting together this very inspiring and stimulating symposium. So I'll be talking today about a set of problems that fall on this spectrum between electrocatalysis and electrosynthesis. I think there are many problems that we consider to be strictly electrocatalysis, right? These are things like oxygen reduction, working with nitrogen, CO2, water chemistry. There are a set of problems that we tend to think about as electrosynthesis, things like epoxidation, coupling chemistry, et cetera. I want to try to show that continuum between electrocatalysis and electrosynthesis and really make the case that there's strong synergy between these spaces and a reason to be working between these two fields to see progress on both sides. So what's very motivating for our group is an understanding of what the carbon footprint of chemical manufacturing looks like. On this plot, on the y-axis, we have greenhouse gas emissions, and on the x-axis, we have production volume. I think there are two major things to take away from looking at this plot. The first is that ammonia actually has its own axis. Its global greenhouse gas emissions are so large that you would just lose resolution for all the other chemicals if you were to put this genuinely on a single set of axes. So there's no way to solve this decarbonization problem unless we do something about ammonia. But the next thing to realize is that if we are genuinely looking for deep decarbonization of chemical manufacturing, then we have to do something about the other 17 molecules shown on this plot as well. So we need to develop routes for decarbonizing ethylene, methanol, ethylene oxide, BTX. These are diverse chemicals that each create their own carbon footprint in a very different way. For some of these, it's because we're trying to make hydrogen for a reduction step, and in the process of steam methane reforming, we make CO2. For others, it's process heating. And so there are many unique places from which the emissions arise, and these will require specific new processes that help to decarbonize their production. So I want to start just by painting a landscape for paradigms in chemical synthesis and try to articulate where I think there's room for a new paradigm in chemical synthesis. So we've heard today about biosynthesis in the context of ammonia specifically. So Shelley told us about nitrogenases. So biosynthesis is using nature's machinery for trying to do chemical synthesis. On the other end of the spectrum, on the far right-hand side, we have total synthesis. And so this would, of course, be a desire to try to make a chemical beginning with commercially available precursors. So in the context of making ammonia, that's a lot like doing the Haber-Bosch process. You're starting with methane, you're starting with water and nitrogen, making ammonia. You've satisfied your desire to do this with commercially available precursors. There are, of course, methods in the middle, things like semi-synthesis, which combine aspects of both routes. You might take something that's partially made through biosynthesis and then complete that with synthetic steps in order to get it all the way to your desired target. What we'll be talking about today is a paradigm in which instead we are interested in the complete synthesis of a molecule beginning from just CO2, nitrogen, and water. So these are our starting synthons from which we want to build bottom up to the chemicals that we interact with in our everyday lives. So I think it's important to emphasize here, just as is the case for total synthesis, with total synthesis we often develop a methodology that starts with these commercially available precursors and gets us somewhere. But if we look, for instance, at many of the molecules that we use today, they're made, for instance, in semi-synthetic routes. So you can look, for instance, at Taxol. There have been numerous total syntheses reported, yet today we make it in a semi-synthetic route, but which has benefited greatly from total synthetic efforts. We've taken so many steps from these total synthetic efforts and applied those towards these commercial semi-synthetic methods. I want to argue here that even though this paradigm strictly limits us to CO2, nitrogen, and water, which is very restrictive, we can use that knowledge for functionalizing molecules that fall even outside this paradigm. So we hold ourselves to this strict paradigm to help further the science, knowing that the outcomes of this work could have impact beyond these three molecules alone, or lead to functionalization steps of molecules that even come from petrochemicals in a sustainable fashion. So we're starting here, for instance, with nitrogen, finding ways to make that nitrogen into ammonia, taking CO2, making carbon monoxide, and making ethylene, and then finding ways to start to stitch together molecules like ammonia, CO, ethylene, to make more complex molecules. So one interesting problem that I'll share is how you can actually use water as an oxygen atom source to do reactions like epoxidation or O atom insertions in CH bonds. So we're finding ways to use these sustainable synthons for chemistry. So we'll start out first by looking at nitrogen atoms specifically. How can we make ammonia beginning with N2? We'll then build on that, looking at carbon dioxide as a carboxylation source. So if you're at a C2 or a C3 or something a little larger, how could you conceivably make that into something that has one more carbon atom? And then finally, we'll look at O-atom transfer. How can you use water as your source of oxygen atoms to introduce more useful functionality, which I think will actually push us techno-economically in a very useful direction. So important cross-cutting themes that will come out throughout this discussion are the importance of thermodynamics. We heard a lot about this yesterday, so I think this is going to be a very important point to emphasize. And as chemical engineers looking at the energy and mass balances, that this can have a pretty important and big contribution towards understanding the viability of these methods for synthetic chemistry. So we'll focus in first on this nitrogen reduction question. So we're interested here in replacing or finding methods by which we can use voltage in the place of pressure. So we're looking here at the Haber-Bosch reaction, nitrogen plus hydrogen going to ammonia. This is a thermodynamic map that shows us the types of conversions that we can expect in this reaction. So we've plotted here the conversion X as a function of temperature and pressure. These are the conventional handles that we have in this reaction. So the conversion here is defined as whether we're at reactants or products. If we are at a conversion of 0, this means that we are purely at nitrogen and hydrogen. It means that we are entirely at nitrogen and hydrogen. So those are the regions on this plot which are red. Whereas if we are at a unit conversion, a conversion of 1, we've gone entirely to ammonia. And so those are the regions on this plot which are red. So I may have swapped the colors in which I just said, right? So red means unit conversions. You've gone all the way to products. Blue means you're entirely at reactants. So I just want to make sure those colors are clear on this diagram. So we'd love to be in the bottom left-hand corner of this plot, right? That's where the conversion appears to be ideal because this is an exothermic reaction. But we know that the kinetics are not favorable, so one is forced then to go to an elevated temperature, perhaps about 400 to 500 degrees centigrade, and that's a point at which kinetically these molecules actually start reacting. But the thermodynamics are no longer favorable. We can see that very clearly on this plot, that we're in a deep blue region of this plot where conversion is negligible. And so the way that we make all our ammonia today is by pressurizing this reactor. Pressurization allows us to recover conversion. We go up to about 200 to 250 bar. And this is how we make all the world's ammonia today, with about a 15% single pass conversion. So this is a real testament to engineering, right, that we're able to feed the world through a reaction of this sort. We can consider instead doing this electrochemically. So let's replace pressure on the y-axis here with voltage instead. We can start perhaps at the same temperature of about 500 degrees centigrade and apply about 1/3 of a volt. And you'll see here why voltage is so special as a parameter in doing this reaction. That when you apply pressure, you follow contours of reactivity. You can see that going up here. You keep applying more and more pressure, and you just remain in the same blue region. You'd have to go to a ridiculously high pressure, which is impossible to industrially apply, to get to anything that starts to look like a unit conversion. You look at this electrochemically instead, and it is abundantly apparent as to why voltage is so powerful. It allows you to cut across thermodynamic contours. So 1/3 of a volt actually gets you to a very good place in this thermodynamic energy landscape. And we also know as electrochemists that applying a voltage helps not just the thermodynamics, it also helps the kinetics of this reaction as well. So you can, in principle, come back down to a lower temperature. Lower than 200 degrees C, even room temperature, those are the types of methods we're pushing here. So if electrochemistry has a special effect for being able to make nitrogen and hydrogen into ammonia, it's useful to consider, well, why not use water instead? Water would be the most sustainable source of hydrogen atoms. This hydrogen here, of course, comes from steam methane reforming. That's where the embedded CO2 footprint is. We could get it from water electrolysis. But we can think about the comprehensive thermodynamics when these two steps are put together, when you have water plus nitrogen going to ammonia. So we can look at this thermodynamic question. This is an unsurprising result. This is why we sleep well at night, knowing that the oceans and the sky are not reacting with each other and making enough ammonia that we would not be able to see the world. We'd be blinking furiously. But this is good, right? So we can stand by what we're saying here. But you know what I'm about to say, which is that electrochemistry is very powerful as a methodology, and you can reach conversions that are useful at relatively modest conditions, right? So a volt is all it takes, right, in order to shift the equilibrium of this reaction to a useful place. And so this comes back to our discussion yesterday, right? There are reactions that you can do electrochemically or you can do thermochemically. This is a reaction that you cannot do thermochemically, right? You would have to go to a set of conditions that are so ridiculous that it wouldn't possibly make sense. And so if we care genuinely about decarbonization and we care about being able to do reactions with modular and distributed feedstocks, this is a reaction which the conventional handles of temperature and pressure cannot get you somewhere useful. So what I showed on the previous slide is a purely thermodynamic argument with kinetic statements that I made on top of that. So the plot's going to be misleading, right? You can look at a plot like that and walk away thinking that this should already be possible. We've already heard about this starting yesterday and continuing today, that this is a very hard reaction to do, right? This nitrogen triple bond is quite humbling when you try to look at it from a catalytic perspective. So we've been working in our lab on a lithium-mediated route. We heard from Tom yesterday about a batch process through which one can convert nitrogen and water to ammonia at exceptionally high Faraday efficiencies. I think that's been very inspiring in the field in terms of a catalytic, or in terms of a cycle-based methodology that works well for this reaction. We're building here on a report published by Sunetto in the 1990s, showing how you can use lithium-mediated chemistry in a continuous fashion to drive nitrogen reduction. And so in this particular system that we're working on, a continuous implementation, you can see here how we're plating lithium atoms to make lithium metal at the interface, making a very thin layer here. I've emphasized nitrogen transport. This is because even though you may think that I'm here to tell a catalytic story, transport ends up being exceptionally important. So this nitrogen is moving towards the surface. We're forming lithium nitride. That lithium nitride is then protonated by a donor in solution, making ammonia, which then naturally evolves. So we're leveraging here the very unique reactivity that lithium metal has with nitrogen. It's the only metal which reacts with nitrogen to make a bulk nitride. And that can be usefully leveraged, building also on a lot of knowledge that we have from lithium-ion batteries and lithium metal chemistry. So I think this is a great interfacial problem that benefits from interdisciplinary stakeholders. We can look here at the mechanism, and this is where our lab has contributed significantly, is taking a reaction which just looks like a very complex, messy, heterogeneous reaction, and being able to break this down into elementary reactions, showing how lithium ions are plated to lithium metal, how the key selectivity determining step is whether that lithium metal undergoes a nitridation reaction to make nitride, or whether that lithium metal directly reacts with a proton donor to make hydrogen. And we can control this to really go towards lithium nitride and then eventually direct this towards making ammonia. So I want to emphasize this transport aspect. Nitrogen is a sparingly soluble reagent, right? You're around 1 millimolar in water, several times that in an organic solvent. So transport is definitely a critical issue. So our lab has been working on making new architectures for lithium-mediated nitrogen reduction, which allow you to not only produce enough ammonia that we know it's not from extraneous sources, but enough that we actually hit a transport limit. And the new architecture actually allows us, by improving gas-liquid contacting, to go above that transport limit. And so that's shown here, comparing the different continuous methods that have been reported before for ammonia synthesis in terms of their production rates on the y-axis, their Faradaic efficiencies on the x-axis. And you can see that this understanding of coupled transport kinetics is intrinsically necessary to reach much higher production rates. So we talked yesterday about what it means to parametrize our science, to put it into metrics, and that it's very easy, right, to select metrics that just simply make your science look good, that don't really address genuine fundamental questions. I think this is a case where mechanistic understanding of how this works, of coupled transport kinetics, allows us to quantitatively then compare how this looks compared to other systems. And I think that's the context in which metrics genuinely need to be used. These are N15 labeled results, so that's a very important point that was raised yesterday, that you need isotopes. But what's remarkable is that for a set of chemistries where usually you're just wondering if you've made ammonia and you need isotopes to somehow even confirm if you've made it, we've actually hit the transport limit and broken the transport limit. So this is a lot of ammonia that we're making in the system, about 10 milliamps per centimeter squared of partial current towards ammonia. So I think this lays down a framework by which coupled transport kinetics can be used to develop more effective systems for fixing nitrogen electrochemically. So if you make this ammonia, then the question really is, what do you want to do with it? I think there are many different contexts in which ammonia is useful. One can think about this in terms of chemical synthesis. That's what I'm emphasizing here. That if you have ammonia, you can now access amino acids, hydrazine, cyanide, urea, nitric acid. Many of these are thermochemical routes, but you're taking one of the most energy-intensive steps, and now you're coupling this to a lot of existing infrastructure. But I think there is also motivation for making multi-step electrochemical, fully electrochemical unit operations. So our lab is looking very deeply at how you could, for instance, do some of these secondary chemistries electrochemically, some of which require 850 degrees centigrade or 1200 degrees centigrade. There is a reason for trying to find more benign conditions for running these types of chemistries. So the second part I want to tell you about here is now that we've talked about how to effectively and sustainably source nitrogen atoms for synthesis, if you can get to ammonia, you have a good way of introducing N atoms for a lot of molecules that are of interest. What about carbon atoms, right? We've heard a bit about how to make CO2 into CO, into ethylene, and molecules of this sort. But can we start to make larger products which involve carboxylation? So the direct use of carbon dioxide in chemical synthesis is pretty underdeveloped, especially for industrial use at large scales. I show two examples here of forming, for instance, carbon-oxygen bonds. This is in the context of industrially reacting ethylene oxide with CO2 to make ethylene carbonate. You can also make carbon-nitrogen bonds by reacting ammonia with CO2 and making urea. Making CC bonds from CO2 industrially is something that's pretty underdeveloped. You'd have to go through CO. So if you want to avoid the CO intermediate, this is something that we don't really have very good ways of doing. So ideally, for instance, we'd like to be able to make terephthalic acid or amino acids like phenylalanine. And I've shown here a host of methods by which one may want to try to do this today. And you'll see that they have many shortcomings. In many cases, we're using reactive and unstable organometallics. We're using stoichiometric metal reductants, so literally adding zinc metal or manganese metal to the solution to act as a reductant. While that works for laboratory scale methods, this is something that you could never dream of doing for a commodity scale reaction, right? You'd be consuming stoichiometric amounts of metal for every molecule that you want to produce. And you can look at the bottom here at electrochemical methods that have been reported. These two require sacrificial anodes. So you're giving up a metal atom at your anode for every useful electron transfer you do at the cathode for carboxylation. So you can see across the board here that there is a big opportunity to figure out how to do carbon-carbon coupling chemistry, especially for carboxylations in what I've shown here. So our lab has been working on these sorts of methods. I show here something which is along the way. This is still something that's not ready for commodity chemical synthesis, but it's starting to show us how to get rid of the sacrificial anode, which cannot be tolerated for commodity chemical synthesis. And so in this sort of methodology, we're showing how a benzyl ammonium salt can be carboxylated to make this product shown here. This method eliminates the need for a sacrificial anode and has a pretty wide substrate scope. There's still more work to do here, and we've very recently figured out how to get rid of the trimethyl ammonium that's involved here without the need for a sacrificial anode. So this is gradually becoming a more and more sustainable chemistry. I think this is important to emphasize because there will be many cases where we will start with smaller scale fine chemicals and develop understanding of how to do process chemistry and reaction chemistry under those conditions. That's where the margins are, right? There are extremely small margins in commodity chemical synthesis. And these methods will then gradually find their way into making into making commodity chemicals. I think we can learn a lot from the way that lithium-ion batteries have progressed in industry, beginning with something that really was a curiosity for camcorders, for photographic cameras, and that now is something which we all know all too well is going to be at the center of making EVs possible. So if we ignore these verticals just because they're only $10 million verticals and not $100 billion verticals, we're going to miss out on a lot of opportunities for gradually developing technologies and to see them actually be implemented for commodity chemical synthesis. So finally, I want to share just a bit here on using water as an oxygen atom source. This is our third synthon. We now see how we can introduce nitrogen atoms for commodity chemical synthesis, carbon atoms, but I want to show how to selectively introduce oxygen atoms, which I think is also very important. So we're going to look at this in the context of epoxide synthesis. We're showing here methods by which epoxides are made today. One can start, for instance, with ethylene, shown up here, react with oxygen, 270 to 290 degrees centigrade and 20 bar to make ethylene oxide. I really have no qualms with those process conditions. If that first reaction was all that happened, we'd be pretty satisfied and sleep very well at night knowing that this reaction is just fine. It turns out, though, that as you do this reaction, you do, in fact, over-oxidize this ethylene. So for about every 9 ethylenes that go to ethylene oxide, 1 ethylene gets over-oxidized to make CO2. This is why ethylene oxide has the 5th largest CO2 footprint of any chemical that we make today. So this is still a problem in industry. So you can see here this over-oxidation reaction, and this is something critical to be solved. One can also look, for instance, at alternative processes that exist, some of which are lower carbon but have other issues associated with them. For instance, the chlorohydrin process, in which you start with propylene, react with hypochlorous acid, making this chlorohydrin shown here. This chlorohydrin is then reacted with calcium hydroxide, and you make your desired epoxide, but you make a calcium chloride side product as well. So you have this brine side product that you need to get rid of. So it's interesting because hypochlorous acid actually comes from electrochemistry, so that's a win or a check mark in the electrochemistry box, but we're making a stoichiometric side product here, and that's why this process is very much being phased out around the world. One can also use a peroxide-based process, which helps to reduce the CO2 footprint, but you'll see here some of the issues that are inherent to this methodology. For instance, you may use metachloroperbenzoic acid to make a particular epoxide. The only job of this reagent is to do 1 O atom transfer, and you create a stoichiometric product that's a benzoic acid derivative. So this is a big problem to solve. You can use peroxide instead, but we all know that mixtures of peroxides and organics at scale are pretty frightening. They lead to a lot of accidents, and so this is the newest chemistry that's being implemented at scale, peroxide-based epoxidation route. So we know that there is still so much more room for improving this process. And so this is the context in which we wanted to try to learn how do you use water as an oxygen atom source. Let's not use peroxide, right? Peroxide has led to way too many accidents. There's a big opportunity for improvement here. In this reaction, we would start with an olefin, react with water, make the corresponding epoxide, and to maintain the mass balance, we make hydrogen at the same time. You can look at the anode here, where we are oxidizing water. So we're generating protons, we're generating electrons. We have a reactive O atom that's generated, which will transfer to this olefin to make the corresponding epoxide. The protons go across the cell, the electrons go through the external circuit, and we make hydrogen on the other side. So I think staring at this overall balance is important because you'll realize that this is just water splitting in many ways, right? You're taking a water molecule, you're breaking it apart, you're letting those those H atoms come together, you're making hydrogen, but instead of letting those O atoms come together, you're placing them on another molecule. And so putting these O atoms together is something that we've struggled with a lot as a community, right? We always talk about how making that oxygen-oxygen double bond is hard. Why not just not make it instead and place that O atom on a different substrate, right? This is something which could make a product which is valuable on the other side, right? This comes back to a point that Bill Toomas made yesterday about what are we doing on the other side of the cell? If only one electrode is making a valuable product and you're making O2, which you just vent to the universe, you're wasting half your cell. So place those O atoms on a useful molecule and see if something can be generated that's of value, right? That's the applied reason for doing this chemistry, although there are so many fundamental questions to answer here. So our group has shown this particular reaction for the first time. I show manganese oxide nanoparticles here, which are able to drive this epoxidation reaction at the anode. You can see here the Faradaic efficiency for epoxidation as a function of potential. And when you get to a reasonable voltage here, you're able to do send about 1/3 of the electrons towards making an epoxide at this interface. So we've been able to gradually improve this. We're now up to about 50% with a somewhat fancier catalyst. But I think there's a clear path here for figuring out how to use those O atoms on the other side of the cell to do useful organic chemistry. So we've spent a lot of time understanding the mechanism of this reaction. I show here what we think this looks like in this particular context, that we believe a manganese oxo is the key intermediate, that we do pre-equilibrium epoxidation, which is very unusual. This is something which feels quite non-intuitive to us. But what I really want to emphasize here is that we have so much knowledge from water splitting chemistry, right? This is knowledge that's deep in the electrocatalysis community. We can take all that mechanistic understanding of how manganese oxide does water splitting, and we can now apply that towards doing organic electrosynthesis, right? We can do epoxidation chemistries if we intercept the right intermediates. So knowing that there is a manganese oxo intermediate from water splitting in pure water allowed us to hypothesize that this could possibly work for epoxidation. So we can translate and leverage all that knowledge. I think this is a compelling case for why we need to be at the interface of electrocatalysis and electrosynthesis to make progress on these problems. I want to point towards the energy balance here as well, right? We've talked about the mass balance, but the energy balance is also important, right? So if we're doing water splitting, we're at about 1.2 volts. If you do O atom transfer to an olefin, this overall reaction here, this has a cell potential of 0.8 volts. So this integrated understanding of what's happening on both sides of the cell, it helps not only the mass balance, it also helps the energy balance in the system. You could conceivably, with a good enough catalyst, cut the energy input to this sort of process of doing water splitting by a third. So this could possibly be some of the cheapest hydrogen that we could make. It's important to be completely transparent about the fact that the amount of hydrogen we need to make for the whole world is way, way more than the amount of epoxides you need to make. But incrementally, this could be some of your cheapest capacity for hydrogen production. So I think it's important to not ignore it. All right, so just a few points here as we round up about what I think the near-term future and long-term future for this field looks like. Bill Toomas mentioned yesterday the notion of horse parity and grid parity. I want to argue for the importance of methane parity in chemical synthesis. So you can look here at the cost of electricity relative to natural gas on an energy basis, purely an energy basis. And you can see here that electricity is 3 to 5 times more expensive than natural gas at present. There are certainly many electrochemical applications which are already technically economically viable. Even some of the commodity chemicals that I mentioned are ones which at today's electricity prices can be viable, some of them. There are others which based just on the amount of energy you need to put in are going to be too expensive to do until you close this gap and reach methane parity. So you can see this on the right-hand side, looking at the cost of hydrogen as a function of electricity cost and capital cost. If we were to reach methane parity, that'd be around 1.5 cents per kilowatt hour. So that would get us far enough to the left here that we could start to tolerate somewhat higher capital costs in order to compete with methane in order to compete with hydrogen that is derived from methane. So we can look just here at the end at what the levelized cost of electricity looks like. And I want to emphasize where methane parity falls on this plot, that we see how much electricity prices have dropped for different sources, whether it's wind, photovoltaics, onshore and offshore wind. And you can see here that methane parity is a pretty daunting target, but that we are getting very close in many contexts to touching that. If you look at the auction prices for electricity, this is why for so many processes that we've tried in the last decade to electrify and have failed, this is why it's going to be different moving forward. So when we look at electrochemical unit operations, I think we can consider what we've tried in the past and made work, right? These are things like chlorine and adiponitrile. I don't expect this to be readable in the whole audience here, but I just want to emphasize that on the left-hand side, we have things like petroleum, natural gas, oxygen, nitrogen, SO2. That leads to commodity chemicals, things like benzene, xylene, toluene, chlorine, etc. Secondary commodity chemicals like terephthalic acid, vinyl chloride, acetic acid, leading to more advanced chemicals and final products. So that's just showing left to right how we start with the very basic feedstocks of the chemical industry and get to things that we actually want to sell. So there are two things here which are made electrochemically today, chlorine and adiponitrile, at the scales that are shown here. We've talked today about how we can make, for instance, ammonia, ethylene oxide, carboxylation routes that could lead to terephthalic acid. We've talked during this workshop how to make CO and hydrogen. So we're starting to see that we are developing routes towards quite a few things that fall towards the beginning of these value chains. And I think that's very important. But there's so many more targets that remain here for which we need to develop new electrified routes to enable more sustainable synthesis. So with that, I'd like to thank the students and postdocs in our group who did all this work. Everyone here contributed to things that I talked about today, always inspired by their creativity and resilience in the face of very difficult questions. And with that, I'd be very happy to take any questions that you have.
I think yesterday we saw a lot of galvanostatic electrosynthesis, and it looks like you're actually doing things potentiostatically. Have you tried to do it galvanostatically? Do you have selectivity issues or?
Yeah, so there are actually some methods that we do run galvanostatically, which I didn't emphasize here. Ammonia synthesis in particular is one, just because the reference electrode chemistry in this non-aqueous system is actually a little bit difficult in this particular case. We do find there that we're able to get much better control galvanostatically. Some of these other cases, we do, in fact, do them potentiostatically, just because there can be different outcomes for the reaction in terms of selectivity if we do run them galvanostatically instead.
Comment and a question. So the comment is the two big chemicals that you want to decarbonize are iron and concrete, right? You do those, that would be spectacular. The question is, how much, I was still a little confused about the lithium situation there. How much extra energy do you have to put in to re-reduce the lithium anion complex that you've made? Isn't that quite a bit?
Absolutely. So if you look at the thermodynamic cycle and how much energy you need to get to lithium metal before you then fall down this free energy landscape, you are capping yourself at a 30% energy efficiency in this approach. I think there's some fantastic techno-economic analyses that show where we need to be for distributed ammonia production relative to Haber-Bosch. Haber-Bosch sets a very high standard for energy efficiency, right? 60 to 80%. It's quite remarkable how well it works. What we can tell from the early techno-economics is that it's clear that we can go to much lower energy efficiencies and still maintain viability here. So I don't think that thermodynamic limit is actually, I don't think that is what's going to kill this system. There are other things which I think could lead to more trouble.
Hey, thank you so much for a beautiful talk. So the chemistry you do, the conversion of the benzyl ammonium salts to carboxylic acid, just the suggestion that you can easily separate the ammonium by replacing the ammonium salt with imidazolium one. It's a process called BASIL. It's an industrial process developed by BASF that they replace ammonium with imidazolium. You can easily protonate them, and it forms two phases with your final product.
Awesome. Thanks. That's an excellent idea. Thank you.
Hi. Mark Jones from Dow Chemical. So I have a comment and a question. The comment, PO, you should go after it. We'd love to have better ways to make that. EO, I think we don't run the processes to maximize selectivity. We run them to maximize unit capital conversion. So the selectivity that you can attain is above 96%. We don't operate there because it's not economical to do so. So that's a little bit. And the other thing on the EO is the EO footprint carries the ethylene production along with it, which is why it appears so high. But my question is, one of the things that frustrates me as a chemist is that industrial processes where we attach ammonia to something don't work very well. So what we inevitably do is we start with ammonia, we oxidize it to nitric acid, then re-reduce it back. So I'm curious as to whether there are electrochemical ways to short circuit that attachment of nitrogen to structures, and also whether you could make nitric acid directly if you can make ammonia. Go the other way rather than reduce but oxidize. Thank you for a great talk.
I completely agree with you, Mark, about the fact that we jump all over the redox spectrum in chemistry today, right? We start with methane, we go all the way across to CO. So from the perspective of the carbon atom, we've gotten pretty oxidized. Then we'll go from CO and we'll make methanol, and then we will oxidize that methanol to make formaldehyde, right? We're jumping all over the redox spectrum. The same is true for nitrogen chemistry. We start with nitrogen, we go all the way to ammonia, we come back to nitric acid, and then we do some chemical synthesis that leaves us somewhere in the middle, right? It's a pretty convoluted way in which we do things, but it works because of techno-economics in the way that you mentioned before, right? So looking at the utilization of ammonia specifically, we do believe that there are methods by which you can avoid needing to attach the nitrogen atom to an oxygen atom and instead more directly use it. So that's a lot of what our lab is working on right now. Is figuring out how do you perhaps oxidize that ammonia to make a reactive radical, how do you do condensation reactions that allow you to utilize it. There's a lot of opportunity there for streamlining chemical synthesis by developing those routes.
So the manganese oxo unit is great at catalyzing oxygen evolution, but photosystem 2 is rebuilt every 30 minutes. And you really don't get long durational stability when you're doing it electrochemically. So are you seeing stability for your Mn3O4?
Yes, so we've looked at stability in particular, given the fact that manganese is notorious for how it can change states over time and lead to degradation. What we find when we do, for instance, a 4-hour batch test is that all the reduction in activity over that period of time is just because of conversion. So what we see in terms of decrease in formation of the corresponding epoxide is simply because we were depleting substrate. So if you replace that with fresh substrate, it'll continue at the same pace. So we're not under purely aqueous conditions. We're in a mixed electrolyte that appears to do something to stability here that we don't yet understand. But there's a lot to do from the perspective of synchrotron studies to understand why exactly that is here.